Hi students, welcome to online lecture on material testing lab. Title of the experiment is to conduct tensile test. Aim of the experiment is to conduct tensile test on mild steel specimen and to find stress, strain, Young's modulus, yield stress, ultimate stress, breaking stress, percentage elongation and percentage reduction in area, and to plot a graph of stress versus strain. Apparatus required are universal testing machine, micrometer and vernier caliper. So before conducting the test, we are going to measure the diameter of the specimen, that is diameter within the gauge length, gauge length, overall length, grip diameter, and after conducting the test we are going to measure the final diameter and final length of the specimen. Now consider a bar of diameter D which is acted upon by a tensile load. We have studied in chapter of simple stresses and strains that whenever some external system of forces acts on a body, it undergoes some deformation. If a body is stressed within elastic limit, the deformation entirely disappears as soon as the forces are removed. It has been also found that beyond the elastic limit, the deformation does not disappear entirely even when the removal of the forces, and there remains some residual deformation. We study this phenomena in a greater detail referring to a tensile test or stress strain diagram for a mild steel. Take a specimen of mild steel bar of uniform cross section. Let the bar is subject to a gradually increasing pull as applied by universal testing machine, and if you draw a graph of stress versus strain, OA is straight line which represents that the stress is directly proportional to strain. Up to point B, Hooke's law holds good. Up to point B is elastic limit. If the specimen is loaded beyond the elastic limit, the strain increases more quickly than the stress. Sudden elongation takes place without appreciable increase in the load. This phenomenon is called yielding. The stress corresponding to point C is called yield stress. After B point, the material shows the plastic behavior. From point C to D is perfectly plastic behavior of material. If the load on the specimen is removed, then the elongation from point B to D will not disappear but will remain as a permanent set. At point D, the specimen regains some strength and higher values of stresses are required to higher strains. From region D to E is region of strain hardening. After E, the gradual increase of length of specimen is followed with a reduction in area. At point E, the stress attains its maximum value and is known as ultimate stress. After that, neck is formed and diameter will reduce. From point E to F is region of neck forming. At F, the stress is known as breaking stress. A later consideration will show that the load required to break away the specimen is less than ultimate stress. The stress is therefore reduced until the specimen breaks. Now we will conduct the experiment and take the readings of load and elongation, and afterwards calculations are done. So in calculation we are going to find load stress, that is load divided by area, strain change in length divided by actual length, Young's modulus E is equal to stress divided by strain, yield stress is equal to yield load divided by area, ultimate stress maximum load divided by area, breaking stress is equal to breaking load divided by area, percentage reduction is equal to original area minus final area divided by original area into 100, percentage elongation is equal to final length minus original length divided by original length into 100. So now we will conduct the experiment.
Students, first we will see the components of the universal testing machine. So this is the upper crosshead, this is the movable crosshead, this is the table which is operated by hydraulic unit. So these are attachments for bending. So these are the handles to fix the job in the job, and this is the frame. And this you can see is the hydraulic power unit, and these are the two buttons to move the crosshead up and down, and these are the buttons to start and stop the hydraulic pump. When you start the hydraulic pump and if you open these two valves, the oil from the pump directly go to the reservoir, and if you close this left valve, the oil will go to the this cylinder, and this table is lifted. You can see the load and cross-side travel, that is the elongation we can see. Load and elongation we can measure here. So this is the digital indicator where we can get load and elongation. Now we will measure the dimensions of the specimen. Afterwards we will fix in the movable jaw, and we will take the movable jaw up and we will fix in the upper jaw. Going to apply the hydraulic load. So overall length of the specimen is 320. Grip diameter is 19.5. So diameter within the gauge length is 15.35, 15.27, 15.24. So we will take the average of this one, and now we will see the gauge length. The gauge length is 107 mm. Gauge length is 107 mm. Now we will fix the job of specimen in the universal testing machine. Now we will fix the specimen in movable crosshead. Now we will move the crosshead up and fix the specimen in the upper jaw. Now we are going to fix the another end of the specimen in upper crosshead jaw. So here we can see fixing of another end of the specimen in upper crosshead jaw. Now we have fixed the specimen in the universal testing machine. Now we will start the hydraulic power unit and we will apply the load. Now these two walls are open. Now I will start the pump and I will close this wall. So here we can see load is increasing. We can see load is increasing and elongation also we can see. Now the load is 112 and it is elongated by 3.56 mm. Specimen is elongated by 3.84 now. So maximum load has taken 130 kilonewton. Now you can observe the neck formation. The diameter will reduce. And at some point it will break. Since the diameter is decreasing, the load to deform also is required less. So load is also decreasing.
Formation.
Now we will stop the hydraulic pump and open this valve so that oil will go to the reservoir. So this is the tensile test. Now we will do the calculation part and draw the graph. So here we can observe a cup and cone type of fracture. This is cup and this is the cone and this is the cup. Now we will join the two pieces and measure the final length of the specimen. Final length and final diameter of the specimen. The final length is 116 mm and the final diameter is 10.5 mm. Now, after measuring the dimensions, final dimensions, we'll now do the calculations and draw the graph.
Students, after conducting tensile test on multiple specimen, in tabular column you can see the load and elongation readings observed during the conduction of tensile test and calculated stress and strain values. So first reading is 6.8. At that time elongation is 0, stress induced is 37.07, strain is 0. So for the second reading 13.15 kilonewton load and strain is 0, induced stress at that load is 71.70, strain is 0. If you observe fifth reading, 45.70 is the load, 0.01 mm is the elongation, stress induced is 249.20 and strain is 0.09 into 10 raised to minus 3. We can observe that the maximum load is 130.45 kilonewton. At that time elongation of specimen is 5.85 mm. If you see the calculation, first find cross section area A is equal to pi by 4 d square, and to find d we have taken average of 3 readings within gauge length and it will come 15.28 mm. Therefore area is pi by 4 d square, that will come 183.4 mm square. Stress for first reading 6.8 into 10 raised to 3 Newton. Load, that is the load, area is 183.4 mm square. The stress will come 37.07 Newton per mm square. So stress for stress and strain for 7th reading. Stress is equal to load divided by area. Load is 48.3 into 10 raised to 3 Newton divided by area is 183.4. Stress will come 263.35 Newton per mm square. Strain is change in length divided by actual length. Change in length is 0.15 mm at that load divided by 107. The strain will come 0.0014. So if you calculate Young's modulus is stress divided by strain. Stress is 263.35 and strain is 0.0014. So Young's modulus within elastic limit is equal to 1.9 into 10 raised to 5 Newton per mm square. So similarly calculate stress and strain values for all the readings, all 21 readings. Yield stress is nothing but it is the yield load divided by area. Yield load is 49.50 into 10 raised to 3 divided by area is 183.4. Sigma y is equal to 269.9 Newton per mm square. So next, ultimate stress, that is the maximum load divided by area. Maximum load is 130.45 into 10 raised to 3 Newton divided by area is 183.4 mm square. So ultimate stress we will get 711.34 Newton per mm square. Breaking stress is equal to breaking load divided by area. So when specimen breaks, at that time load is 100.9 kilonewton. So 100.9 into 10 raised to 3 Newton divided by pi by 4. D here we have taken 10.5, means that is the final diameter we have taken to calculate breaking stress. So breaking stress will come 1165 Newton per mm square. Percentage reduction area is original area minus final area divided by original area into 100. So original area is 183.4 mm square, final area is 86.6 mm square divided by 183.4 mm square into 100, that will come 52.7%. that is percentage reduction in area. Final area, that is nothing but it is pi by 4 into d square. D here we have taken 10.5, that is the final diameter we have taken. So when the specimen breaks, we are going to join the two pieces and we are going to measure the final diameter, that will come 10.5. Next, percentage elongation, that is equal to final length minus original length divided by original length into 100. Final length measured is 123.5 minus 107 divided by 107 into 100, that will come 15.4%, that is percentage elongation. And to plot the graph, we have taken on x-axis strain 1 cm is equal to 10 strain, y-axis 1 cm is equal to 50 Newton per mm square, that is stress. So this is the nature of graph. So this completes the tensile test experiment. Thank you.